Hello everybody. This lecture is devoted to elements of quantum mechanics. First of all, we will summarize properties of microobjects. Microobjects simultaneously possesses the properties of particles and waves, and therefore are neither one nor the other in the classical sense. The microparticle states are characterized by psi functions. The psi function of a free particle is a plane wave. Microparticles should be imagined as spread over the space. The probability density to find a particle in a given place is defined by square of psi function. The velocity of a particle coincides with the group velocity of waves corresponding to the particle state. Microparticles have no defined trajectories in the classical sense. It is impossible to simultaneously measure precisely a coordinate of a microparticle and the projection of its momentum on the same axis. The uncertainties of such measurements are related by the Heisenberg relation. New understanding of the experiment. To conduct an experiment means to change the state of a particle, that is to change its psi function. When we say that microparticles have no defined trajectories in the classical sense, sometimes it is not so straightforward understandable, because we can follow electron trajectory in some experiments, and the question arises how it is possible if we stated that microparticles have no defined trajectory. The point is that if a particle is free and if its energy is large enough, then the wavelength is short, and this is the same situation as in optics, when the wavelength is very short, is tend to zero. We come to geometrical optics, when there is no wave properties at all, no interference, no diffraction, just straightforward projection of light. So this is the same, because if we apply this if we consider this wave properties of a particle, so when a particle is moving in some small domain of space, then in this case this Heisenberg relation prevents of knowing simultaneously, if you remember, momentum and coordinate. This means that in this case we don't know anything about trajectory. And if a particle moves with some energy and in large space, in large domain of space, not is bounded in atom, for example, so we can follow this particle, and we can neglect this wave properties in this case. This is another superposition principle. We studied already some superposition principle in electricity and magnetism, and this in quantum mechanics, the sense of superposition principle is as follows. If a quantum system can be in the states characterized by the wave function psi1 and psi2, so there are different states. One is described by function psi1 and another by function psi2. So the statement is that it can also be in the state characterized by the wave function, which is a linear combination of these two wave functions, psi1 and psi2, with coefficients a1 and a2, which are arbitrary complex numbers. The essence of the principle is as follows. Let L is some physical value which we wish to measure, and if the system is in the state which is characterized by the function psi1, the result of measurement gives us L1. And if the system is in the state which is described by psi2, so the measurement gives L2. Now imagine that now the system is in this state, which is characterized by psi, which is linear combination of these two functions. Then result of measurements will be either L1 or L2 with probabilities defined by coefficients A1 and A2 respectively. Namely, the probability of obtaining the result L1 is A1 squared and the result L2 is A2 squared. You see that actually the result of measurements in this combined state is not predictable. You can predict only probability. You cannot accurately say what is the result of the measurement. You can measure the same value several times and obtain different results with different probabilities. Surprisingly interesting physics at this micro level. Now we need to study some mathematical basis of quantum mechanics, quantum mechanics operators. First of all, what is operator in mathematics in general? In mathematics, an operator is generally a mapping that acts on elements of a space to produce elements of another space. Let's start with, in order to understand this statement, let's start with a definition of function. What is actually function? Imagine that we have two sets of numbers, and one set of numbers is just natural numbers, and another set is the result of applying function x squared. For example, the function consists in squared of numbers. Then to each number in the domain of just numbers, this set of numbers, we can have in another domain, we can find elements which corresponds to each of the elements of the first domain. Just take any number in the first domain, square it, and the result is a member of the second domain. This is function. This is a rule how to obtain elements in new domain, taking original elements from the first array of elements. This is actually a definition of a function. What is the difference with operator? The difference with operator is that in the first domain there are not numbers but functions, and you apply something and obtain another function in another domain. For example, if we look at the operation of taking a derivative, so if this is operator, derivative, so we take some function in one domain, for example x squared, apply this operator and obtain another function again, 2x, after differentiation. So this is how this operator can be understood. This is general mathematical definition. In quantum mechanics, an operator is a function over a space of physical states to another space of physical states. It's a rule, actually, which make a mapping of states in one domain to another domain. Actually, this means each of the states is presented by psi function. So if we apply this operator to psi function, we actually make this a mapping of physical states in one domain and another domain. So if we apply some function, some operator to a psi function, actually we apply this operator to physical state. So this is a meaning of this statement. Now, if the result of applying an operator A to a function is the same function multiplied by a certain number, lambda, this is actually, if we apply operator, we denote operator with this sign. So we apply operator to some function u, and the result is that this function u is just multiplied by some number lambda. So, and if this function u is single-valued, continuous and finite, then it is called an eigenfunction of the operator, and lambda is its eigenvalue. Only so-called Hermitian operators are used in quantum mechanics. This is a definition. An operator A is called Hermitian if for any two functions u and v, the following relation holds. Look, if we integrate this A operator applied to u and multiplied by complex conjunction of v, and this is equal to this, so we substitute v here, and this we also apply this complex contraction to operator, and if this holds, then such an operator is Hermitian. Why we use Hermitian operators in quantum mechanics? Because if we apply this eigenvalue equation, so these lambdas, they corresponds to actual values which we can measure in a quantum system. But any measurement should give a real value, real number. So this it is possible easily to prove that Hermitian operators have real numbers as their eigenvalues. So Hermitian operators are used in quantum mechanics because their eigenvalues, which corresponds to physical values, which evidently are numbers which can be measured, and so they are real numbers. And the real numbers are eigenvalues of such Hermitian operators. Now we can summarize what we know from quantum mechanics, and this here are postulates which are used to interpret what we observe in quantum mechanics. So most of them we already know, but to summarize all of them, the state of a particle is characterized by the wave function psi, which satisfies Schrödinger equation. So we can obtain this function psi from Schrödinger equation. Each dynamic variable is represented by a certain Hermitian operator. Look, if we have some Hermitian operator, and then for any physical value they are different, for example for momentum, for energy, and then we will this eigenvalues will give us the energy or other value or other physical values which are possible in this system, which are solutions of the system. You remember that actually even Schrödinger equation has solutions which produce functions which satisfy requirements to be continuous, finite and single valued, not at any, for example, energy, but for some selected which are called eigenvalues. So these eigenvalues can be found. So again, each dynamic variable is represented by a certain Hermitian operator. The measurement of a numerical value of a dynamic variable represented by an operator A gives one of the numbers, which are actually eigenvalues of the operator A. So in order to find the possible values which the system can obtain, can have, we need to resolve the eigenvalue equation and find these eigenvalues. The probability of, okay, we have different numbers. The point is to know which is probability to find any of them. And the probability of obtaining one or another value of lambda I is calculated by the following rule. Let the un be the eigenfunctions of the operator A, so they satisfy this equation. This is eigenvalues equation. And the system of functions un is orthonormal. It can be proved. It's orthonormal means that it is normalized to unit, and the integral of any function un and um over all the space is 0 if n is not equal to m. Then psi can be expanded in series through this function, because any function can be expanded through series over orthonormal and the complete set of function, and it is complete as well. So it's mathematical issues, and we can just accept that these functions, if they are functions of eigenfunction of a Hermitian operator, so they are also normal, and the system of this function is complete. The probability that the measurement of the dynamic variable represented by the operator A will give the numerical value L lambda n is equal to square of this coefficient, which is here. So this is a rule, how to obtain these probabilities. You see that this the quantum mechanics in a sense produce only probabilities, not exact values, which we can expect to measure. So now we will look at the statistical nature of quantum mechanics. So look, it follows from the meaning of the psi function, and you remember that the square of psi function gives us the probability density, so that quantum mechanics has a statistical nature. Indeed, the square of the magnitude of the psi function gives the density of probability of a particle being in the relevant place in space. It does not allow us to determine the whereabouts of a particle in space or the trajectory along which a particle is traveling. The psi function only helps us to predict the probability of finding a particle in different points of space. On the other hand, as far as the probability is known, look, we know how to find this probability. So as far as probability is known, it is possible to find an average value of a dynamical variable A. Indeed, we take all these numbers which are eigenvalues, which can be the system can have, and take them with weight of probability of each of them, and then it gives us average value. In the state of a quantum system, if the state of quantum system is characterized by a function psi, then the average value of variable represented by an operator A is as follows. Now we will prove how it can be, how this is equal to this. So this is equal to that. Indeed, psi and psi complex conjunctive can be expressed through the following expansions. Okay, psi is here, and sorry, should be psi, this is asterisk. Psi with asterisk is here. Then we substitute them here, and A average, we just put this here, this here, and this with asterisk we substitute here. Now, as far as this operator acts only on function, not on coefficient, so we can insert it here. Look, we move it here. But this sum, this is actually AUM. It gives us lambda m, because this is eigenvalue lambda m um, because look, this is this equation. If we apply operator on the function, we have eigenvalue equation, this eigenvalue multiplied by function. So we have here it. So this result in lambda m um. Now look, if we integrate it, and we keep in mind that ul and um are orthonormal. So this integral, when we multiply these two sums, we have different we will have terms with different ul and um. And if L is not equal to m, as these functions are also normal, so the result is 0. If L is equal to m, then the result is 1. What we have in this case, we have this result. Then when m is equal to L, we have 1, so it is L squared, and in this case m is equal to L. So we arrive from this relation, we arrive to that relation. This means that we can obtain this average value of some physical quantity even if we know psi function which describes the system. Now let's look at some particular cases. What are operators of some physical dynamic variables? We'll first start with operator of coordinate. We already mentioned that operators representing dynamic variables must be Hermitian. The choice of their specific type is determined by the agreement of the results obtained with their help with the experiment. Let's find the average value of a coordinate x. Look, in order to find average x, we have take x which with weight of probability it can be found. If we look, what is this psi with asterisk psi dx? This is probability to find x in element dx, because psi asterisk psi gives us probability density multiplied by dx gives us probability. So we integrate, so we take x with weight of this. This is just definition of what is average, nothing more. But we remember that here is a rule how to find average. We just rewrite this, moving x in between this and that, and we see that the shape of this integral is actually the same as this. But here in between psi with asterisk and psi, we see operator of this variable a. So this is operator of this variable x. This means that applying an operator of coordinate x to a function is reduced to multiplying it by x. So this is a one-dimensional case, of course. So look, if we apply x on fx, it means that just multiplying x and fx. Next is operator of momentum. We remember that according to de Broglie hypothesis, a free particle with a projection of momentum of px is represented by a plane wave. Therefore, the solution of the eigenvalue equation, this is the eigenvalue equation for momentum. So operator of momentum, projection of momentum on x-axis, applying to psi is just multiplying eigenvalue of px and psi. So the solution should be of a form of plane waves. This is a plane wave. We remember what is omega in the Broglie wave and what is k. We substitute here omega and instead of omega e over h and px instead of k, px over h, and we obtain this. Now, if we compare what we have this psi, if we look at this function and try to look at this equation and try to guess what should be this operator in order this function satisfy this equation, we see that it should be d over dx, h over I. Indeed, when we take a derivative from this, we have look here, d over dx, we have this will be px, and again this will be the same function here, and h over I will vanish with I over h here. So in this case we see that the shape of the operator should be as is shown here. Now the same is of course for other axes, I mean y and z, and the total momentum is a vector. So this operator is vector operator, and it looks like here. So this is element for px, it is for y, and this is pz, and total it is, if you remember, this number operator, and this is final form of operator for momentum. Next is operator of energy. In quantum mechanics it is used in Hamiltonian form, and usually is called Hamiltonian. In classical mechanics, Hamiltonian is a total energy expressed through the momentum and coordinate of a particle. For a single particle, Hamiltonian is just, this is kinetic energy, this is potential energy. And again, this is energy represented through, expressed through the momentum and coordinate. Relations between operators in quantum mechanics are the same as the relations between corresponding dynamic variables in classical mechanics. This statement is just taken from experience. So it was found that the same relations which are observed in classical mechanics between variables are held in quantum mechanics for corresponding operators. Consequently, the quantum mechanical Hamiltonian is obtained by substitution of the momentum operator in the above equation. We have this momentum operator here, we substitute it here, and this is a result. This is Hamiltonian equation. Actually, if you look at this result, and it is just for your homework, write down eigenvalue equation for Hamiltonian operator, and you will obtain Schrödinger equation. Now, operator of an angular momentum. In classical physics, again, momentum is this vector product r and phi and p. And this is projection on x, y, and z. Substituting the operators corresponding to dynamic variables gives us. You remember that for coordinates we have just multiplying coordinate, and for momentum we have also what is actually this operator. Result is as follows. Now, in order to understand how all this quantum mechanics works, we will consider some quantum mechanical systems and we will start with quantum harmonic oscillator. First we will consider classical oscillator. Classical oscillator is a body of mass m which can oscillate. When it is in equilibrium position, it has coordinate x equal to 0, and if it is shifted from this equilibrium position, some force is exerted which is F minus kappa x. The potential energy of the system is U is kappa x squared over 2, and force and potential energy, you remember how obtain force from potential energy. Force is minus gradient potential energy, and you can find also potential energy by integrating of force. If we resolve Newton equation which corresponds to this classical case, we will obtain the frequency of oscillation, and this frequency is square root of kappa over m. The system has only one frequency, and it oscillates with this frequency, and the amplitude is depends this amplitude of the initial condition, of course, but during the oscillations all the time in each oscillation we have transformation of kinetic energy into potential energy, and vice versa. When this body is in its maximum or minimum position, then potential energy is maximum and kinetic is minimum, and when it goes through equilibrium, it has maximum of velocity and maximum of kinetic energy. Here is no potential energy in this point. Potential energy is 0, and each oscillation is associated with transformation of energy from kinetic to potential energy and back. This is classical picture, and if we have the same, of course not a body on spring, but some system, quantum mechanical system, which can oscillate. In order to resolve this problem, we need to apply, as usual, we need to apply Schrödinger equation. Schrödinger equation, if you remember, for stationary state means that this state doesn't depend on time, and in this case we have potential energy kappa x squared over 2 is substituted here. I have to remind you that in quantum mechanics, movement or change of state is movement, and if a system even oscillates with some frequency and its energy is conserved, so the movement from the point of view of quantum mechanics, there is no movement, so the state is stationary, even if from the classical point of view some movement occurs. Well, if we resolve this equation, it will produce us function psi, and we remember that in the case of Schrödinger equation, it has solutions which satisfies requirements for psi, standard requirements for psi. Psi should be continuous, single valued and finite, and this happens not at each e, but at e's which are called, as we know already, eigenvalues, and eigenvalues for this system, if we resolve this equation and find possible values of En at which this solution satisfies standard conditions, then we will find that En are as is written here. it is and n in this formula, n starts from 0, 0, 1, 2, 3, and so on. It is interesting to note that when n is 0, E0 is h over 2 kappa over m squared, square root, and even at n equal to 0, we have some energy, E0, which is not 0. If we consider what is potential energy here, potential energy is drawn as a parabola, because this is parabola, of course, and the ENs are drawn here, and we see that delta EN distance between two levels, En plus 1 and En, does not depend on n. It is if we substitute here n plus 1 and n and and subtract it, so this does not depend on n. That means that all the levels are equidistant, yeah. That this difference is always the same between levels. And at the lowest level, it corresponds to the case when energy is here. So for this level, we see that even at 0 n, we have some energy of oscillations, and actually some oscillations conserved, and this is a consequence of uncertainty principle, because we cannot fix simultaneously, as you remember, position, coordinate, and projection of momentum on this coordinate. So if we fix this point, so we have some movement, and it cannot be avoided. So this zero oscillations always exist. Now let's consider what is possible emission. Imagine that this system, when it jumps from one energy level to another energy level, can emit energy delta En from the system. Then as E is omega h, so this is quantum of photon. So this omega, the frequency is delta E over h, is square root of kappa over m. And this is in as far as levels are equidistant. So this corresponds to any of jumps from n2 to n1, or from n1 to n0, and so on. All the levels are equidistant. Now, if we try to understand whether it is possible, okay, we stated that there is only one frequency in this quantum system. The question arises, why isn't it possible to jump, say, from n3 to n1? Because in this case, delta E will be doubled, and frequency should be also doubled. Whether it is possible? No, it is not possible. And how can we prove this? First of all, it follows from accurate solution of this equation, but we can arrive at the same result without resolving of equation, just from philosophical principle, and this philosophical principle is correspondence principle. Correspondence principle is a philosophical guideline for the selection of new theories in physical science, requiring that they explain all the phenomena for which a preceding theory was valid. In our case, preceding theory is classical physics, so this correspondence principle requires that quantum mechanics in principle produce the same results which are obtained in classical physics when it is applied to classical case. How can we proceed here for to classical case? Look, when energy of the system increases, it corresponds to increases of number n, and the energy increases, and we remember that the wavelength is inversely proportional to momentum, and so to energy as well. And if it is if energy is increasing, so the wavelength is decreasing. In classical limit, wavelengths should tend to zero. In optics it corresponds to geometrical optics, and in quantum mechanics it corresponds to classical mechanics. Well, if we increase energy, so sooner or later we are very high on energy, and this is already a classical case. If it is classical case, then we can look what is classical prediction. Classical prediction is the only frequency omega 0. This is the only frequency which is attributed to this system. Then in the case of quantum mechanics, there should be also only one frequency. And if there is only one frequency at high energy, then we look that as far as all the levels are equidistant here and at high energy as well, so nothing is specific for high energy. The same should be here. So propagating this, using this correspondence principle vice versa, from classical physics to quantum physics, we propagate the result obtained in classical physics to quantum physics, and thus we can say that if this corresponds to correspondence principle works, so it should be a prediction from classical physics that quantum system should have only one frequency. So somehow this jumps from one level to another through intermediate one are forbidden. Now we will use this, we will look at the working of correspondence principle in straightforward direction. Look, in principle, we in these figures, what we have this limits, classical limits. What are classical limits? Actually, classical limits are amplitude of oscillations. So system, when it spent all the potential energy, so all the kinetic energy which was stored in the moment, it stops and moves back, and so on. So this corresponds to this classical limit. If energy is larger, so we started from larger deviation from equilibrium, then amplitude is also larger, and so on. It is larger and larger. These numbers increases, so En increases, and in classical case also amplitude increases. Look, here we see first of all that the solution of this equation, this is actually solution of this equation for different Ens, En0, En1, En2, En3, and we see that somehow system can be, okay, square of psi is density of probability. So somehow the system can be in the region when kinetic energy was already spent, and somehow it penetrates further beyond the classical limit. And the same is here and at any of number n. On the other hand, This classical limit is already points at which the velocity of the system is zero. So if we ask the question where it is most probable to find the system, the answer is in the positions where velocity is zero, because in this region, in this parts of trajectory of body, it moves with slow velocity, and so it is in this region longer than in the point of equilibrium, which it goes through with high velocity. So if we look at if we try to compare classical and quantum probabilities for harmonic oscillator, what we will find. Classical probability for n is 0 is here. So at the edges of trajectory, there is maximum probability to find a particle, and here in the center is minimum, because this equilibrium point the body goes through with high velocity. So it occupies this region a very short time. And we see that the prediction of quantum mechanics is absolutely different. Maximum is in the center, and minimum are on the in the region of classical limits. If we go further, for n equal to 1, the probability is very strange. So in the center it becomes 0, and there are two bumps here. For n is equal to 2, we also have the system in which there is a dramatic difference between classical probability and quantum mechanical. But when we increase n to large number, n equal to 10 and even greater, we see that if we average all these bumps and dips, we will obtain a curve which is very close to classical distribution of probability. So we can say that this correspondence principle works, that quantum mechanics, when you remember, increasing n is increasing energy, and increasing energy means a shorter lambda, the wavelength, and so we are closer and closer to classical case. And if we tend n to infinity, so we will obtain very sharp, very narrow these bumps and dips, and this curve will be exactly what we obtain in the case of classical mechanics. Now back to this figure, which I already clicked several times. What is this? This is energy dependence of potential energy for molecule. If molecule consists, say, of assume that it consists of two atoms, and r is the distance between the centers of atoms, so the potential energy is like this curve. Somewhere there's a stable point of equilibrium, and if we try to move one atom closer to another, there is force which is repulsive, and if we try to increase the distance between atoms, there is a force which is attractive. So this is a potential well, and the shape of this potential well is very close to parabola, and this means that in this curve it's possible that this molecule has levels of energy like this, and these levels of energy, of course, should resemble the levels of quantum oscillator. and so they are equidistant. And in principle, when a molecule changes its state from one to another, there should be some emission of radiation, and this electromagnetic wave it can be registered, and molecular spectroscopy uses this fact, and so this harmonic oscillator, consideration of harmonic oscillator has also a also practical practical sense. Now we will consider next system, and this system is a potential well. It is very instructive to study the system, because in this case we will see how all this stuff with eigenvalues and eigenfunctions works. What are actually these eigenfunctions and eigenvalues in a simple case of one-dimensional potential well. So what is potential well? Potential well is a region, domain of space in which in some region U is equal, potential energy is equal to 0, and here is infinity and here is infinity. So particle is moving somewhere in between these constraints, or between 0 and L, where L is the width of potential well. Again, as in the case of any quantum mechanical problem, we start with Schrödinger equation. For the region from 0 to L, in this Schrödinger equation we have to substitute U equal to 0, because U is 0 here, and this equation becomes simpler. Now this equation can be solved, and if we look at this equation, you see that it is typical oscillator equation which describes oscillations, and we use it, and the only difference was that usually this was the derivative on t, on time, and here is the derivative on x, but the shape of the equation is absolutely the same. And so we know what is solution. Solution is that if omega is this is omega, so the solution of this equation is psi is a sine omega x plus alpha, with two, because this is the equation of second order, so we have two constants to find, a and alpha. In the case of this well, we have to remember that psi should be continuous, and this means that if it is the particle cannot penetrate from this point to this point, because here is U is infinity, but it cannot just stop here. I mean the psi cannot stop here without some continuous tail in this region y, because if it is 0, okay, what is important? If it is 0 left of L, it should be 0 right of L. Otherwise, it will be not continuous. So in this case, we can say that psi on 0 is, we substitute x0 from this side, and it is equal to 0, and it follows from this that alpha is 0. On the other hand, here should be L. I'm sorry, this should be L. So psi on L is a sine omega L, and it should be 0 as well, because if it is 0 in this region to which particle cannot propagate, so it should be 0 left of L as well. So in the point L it should be 0. So psi on L is 0. This means that omega L is n pi, from which we can find omega is equal to n pi over L. Here n is 1, 2, 3, and so why not n is equal to 0? Because if we put n equal to 0, then we have psi of L is 0 and all the psi at any point will be 0. So psi will be 0 over all the region. Now, if we have this omega, we remember what is omega. So from this we obtain that En eigenvalues for E is here. And for function, this function, we substitute omega and obtain this function. This is eigenfunction, this is eigenvalue. Now, in order to find the constant A, we will normalize the function. So, what is this normalization? As far as particle is definitely in this region, then the probability to find particle somewhere between 0 and L is 1. So we squared psi to obtain the probability density multiplied by the x and integrate from 0 to L to obtain total probability to find particle in the region from 0 to L. And the result we equate it to 1, from which we can, after integration, we can obtain that A is written here. Now look, these are eigenvalues for energy, and this is eigenfunction for n is equal to 1, 2, 3, and here we see that the probability to find particle in some region of this well depends on n. For n is equal to 1, maximum probability, most probable position of the particle is in the middle region of this well. And for example, for n is equal to 2, this point of this region is of low probability to find the particle. So this is a specific result obtained in quantum mechanics approach. And now we, from this consideration, hopefully you better understand what are these functions, eigenfunctions and eigenvalues, and how all this quantum mechanics works. Of course, we considered some one-dimensional case, which is simplest of what is possible. Okay, if anybody will use this, okay, I will correct this mistake in PowerPoint presentation, which I will upload on the site. Next, we will consider penetration of particles through a potential barrier. First, we will consider so-called potential step. Potential step is a region of space, domain of space, in which left of it some border here potential energy is 0, and here it is U0. So it is potential step. We will consider two cases. First case is, for example, if we have a particle which moves from left to right, and its energy is greater than u0. So we will consider this case again as in any quantum consideration of quantum problem. We use this equation, Schrödinger equation, and in this case we consider two ranges from 0 to left and from 0 to right. When x is less than 0, then u is 0. So equation is without u. And this equation is a standard equation, this differential equation with constant coefficients. And we know what is the solution. The solution is here. You know how to resolve such equations. And this is a solution with kappa is here. In the case we have x greater than 0, so in this region we have this equation, and again this is a solution. The only difference is that kappa is different, because here is e minus u0. Look, if we consider these functions, then we in this region we see that these two terms corresponds to plane waves. One wave propagates from left to right, and another from right to left. So for this region there cannot be a wave which travels from right to left. And so we arrived at the conclusion that B2 should be set to 0 in order to vanish this term. Then we have only one wave which particle travels from left to right, and this is incoming wave. Again, at the point 0, in order the function, psi function, would be continuous, its value from left of x and right of x should be the same, and the same holds to derivative from psi at left and right of 0. From this we have equating this and that, we have this, and after differentiation we have this equation, which we derive also from these two equations. From this, when we put x equal to 0, we have a1 plus b1 is equal to a2, and from this we have this result. This is simple algebra, you can repeat it yourself. Then we can find the reflection coefficient. What is reflection coefficient? If we look at the first solution, it also contains two waves. One propagating from left to right. This is actually incident wave, and this is reflected wave, which in principle can arise from this border between these two regions of space, because there is some inhomogeneity. So in principle this could be some wave which reflects from this barrier, from this potential step. And we remember that amplitude of the wave, square of amplitude of the wave, is intensity of the wave is proportional to the square of amplitude. So the reflection coefficient is b1 squared divided by a1 squared. Here is this wave which goes from right to left, which can reflect from this point, and this is incident incident wave. When we substitute, we can use these two relations, and then we can derive this relation, and it will be equal to this result. What is impressive in this result? We obtain some reflection coefficient in the case when energy E is greater than U0. So reflection occurs even so E is greater than U0. So kinetic energy is greater than potential, and it seems that in classical mechanics it will be traveling here, and at this point it had all the energy as kinetic energy, and here it will divide this energy between potential and kinetic. Total energy is the same, and there is enough kinetic energy in order to propagate here in this direction without any reflection. But it appears that in quantum mechanics solution there is some probability that even if the particle has energy, kinetic energy, enough to travel without reflection, there is some probability that it will be reflected. This is specific for quantum system, which differs from a result which we know from classical mechanics. Now we will continue with consideration of the case when E is less than U0. In this case, in the left part, the equation is the same. In the right part, the difference is that this term is negative. Then the solution is without imaginary I here, imaginary 1 here. So this is solution. Again, you know how to resolve such equations, differential equations with constant coefficients. And this is solution, and K is here. Okay, U0 is greater than E, so this term is positive. Now look at this equation. If we increase x, then this term infinitely increases. And so it means that in order to keep the function finite, we need to put a2 equal to 0. So in order the psi2 function be finite, a2 should be 0. Then the probability pi2, the probability density is squared psi. This is equal to 0. So psi squared is proportional to E in minus 2 kappa x. So what we see? We see that the probability density dumps in this region, but it not sharp edge of this probability. It dumps exponentially. So if we draw the probability to find particle somewhere, so it starts from this point to diminish, but exponentially. So in this field there is non-zero probability to find particle in this region, even so E is less than U0. Look, if we use not potential step but somehow organized potential barrier, it differs from this case that it is of finite width. In step it is infinitely long, but here it's finite. And again, if we look at this equation and consider what will happen, we see that in this region the probability to find a particle is exponentially decreasing. But look, it may somehow, exponential decrease means that it is 0 at infinitely far of this point. So it goes down, but nevertheless even here it is non-zero. So there is non-zero probability that a particle will penetrate through the potential barrier even if the energy E is lower than the height of a barrier. So somehow the total energy is not enough in order to propagate if we consider it in classical case. So if kinetic energy is not enough, is lower than potential level or potential barrier, so particle cannot propagate in this field. How it is possible? The answer is that due to wave property of particle, and from which follows uncertainty principle, we actually cannot separate in quantum mechanics at that level, we cannot separate accurately kinetic and potential energy. Why? Because kinetic energy is defined by momentum, and potential by coordinate. But we remember that there is uncertainty. We cannot define simultaneously both coordinate and momentum. So this separation of energy into kinetic and potential in such case is not possible at all. So somehow particle can penetrate in quantum mechanics through barrier. It is called a tunnel effect, and by the way, in your smartphones it is used widely. And if the barrier is a rectangular barrier, if a barrier is of arbitrary shape, then the corresponding calculations show that the penetrability of such a barrier is defined by this equation. So we need to integrate this part of barrier. This is here. And if we integrate it, we obtain the penetrability. So actually probability to find particle which penetrated this barrier. This what we consider. We considered some cases which are one-dimensional, first of all, so they are not in reality they are not met in nature, but they demonstrated some effects which are produced by quantum effects, which are evident when we apply quantum mechanical laws to real objects.